Good morning, children. Now we shall discuss about arrangement of electrons in differentials. This is a fundamental from chemistry. Those who are not very well versed with how to write electronic configuration, how the electrons occupy the differentials, for them it's kind of revision class. Okay, so now see here. So already even in periodic classification of elements we have seen that there are shells around the nucleus, and in each shell there is a rule for occupancy of electrons, and you have the first shell to be K. In K you have only one s orbit, and an s orbit can accommodate only 2 electrons. Then comes the L shell. In this you have S and P orbits both. S can accommodate 2 electrons and P can accommodate 6 electrons. So altogether in the second orbit you will have 2 plus 6, 8 electrons. And then when coming to the M shell, so you have S, P and D. So S can accommodate 2 electrons, P can accommodate 6 electrons, and D can accommodate 10 electrons. Likewise in the third orbit, what are the maximum number of electrons that we can have is 2 plus 6, 8, 8 plus 10, 18. So thus we will write in the first orbit, that is in K shell, you have 2 electrons. Then L shell 2 plus 6, that is S and P. Then M shell you have 2 plus 6 plus 10, that is S, P, D. Okay, then if coming to N shell you have number of electrons in N shell to be 2 plus 6 plus 10, plus then F is also added, where F it is like it is having 7 orbitals and each orbital can accommodate 2 electrons, thus forming 14 to be the total number of electrons. So likewise, so each shell can accommodate a particular number of electrons. Of course there is always a rule that always the outermost orbit can accommodate only a maximum of 8 electrons. But what is this magic? We can see here that if it is M, that is the first, second, third orbit. So in this you have 2 plus 6, 8 plus 10, 18. But what is this rule? What we call as octet rule, that outermost orbit can accommodate only 8 electrons. What is the magic and how it is happening, and how come that we got it to be again 18 here? What is this confusion? So let us come out of that confusion. So look here. So if you take for the first orbit, so this is Euler's diagram which states that how the electrons are occupied. So first electrons always try to complete, fill first orbit, that is S orbit, and then the next shell S orbit. Then comes to the P orbit in the second shell, that is suppose it is in L shell, it will accommodate again. After occupying the S, they will come into P. Then after P, then they will get into the third shell, that is M shell, and then 3S they will try to occupy in 3S. Then after 3S, 3P, that means 2 plus 6, 8 are done here. So when 8 are done here, now you can see in case of the third shell, that is M shell, see already 3S, in 3S you have 2 electrons being occupied, right, filled, totally filled. Then next the electrons will occupy 3P, where 3P is 6. Okay, so 2 plus 6, 8 are done. Then immediately after that, see, it is not coming to 3D. The electrons are not going to enter into 3D. They are going to enter into 4S. See the arrow mark here, after 3P, it is to 4S. So thus what is happening? Now the electrons are jumping into the next orbit instead of filling the vacancies in the third shell. So they are jumping into the fourth shell, and you can see that 4S is filled first, that is 2 electrons are done, and then it is going back to 3D, then it is going back to 3D. So therefore there is no point that any particular shell, if it is going to be the outermost, it cannot accommodate more than 2 plus 6, 8 electrons. Okay, so see here also the case, same case. If you go to the fourth shell, 2 electrons are completed here, 6 electrons are completed. After this it is not entering into D. See, it is entering into 5S. After 5S is filled, then only you will go to 4D. Then only you will go to 4D. So that is the magic behind saying that an outermost orbit can accommodate only 8 electrons. Right. So this is a briefly like S can accommodate 2 electrons. In P you have 3 orbitals Px, Py, Pz, and then each orbital can accommodate 2 electrons. Therefore 3 2s are 6. And here D has 5 orbitals, 5 2s are 10. F has 7 orbitals, 7 2s are 14 electrons. This is how the electrons will accommodate in the specific orbits. Right. Now, how to write the electronic configuration? Electronic configuration means it is something like giving an address of all the electrons which are present inside the atom, where which particular electron is present. Right. Suppose if you take hydrogen, we have only one electron in hydrogen and one proton in the nucleus. So this one electron will be in the first orbit, that is in the first shell, that is in K shell, where you have there only S. So it will occupy 1s1. 1 stands here for the shell. First shell, S orbit, 1 electron. This is the address of the electron in the hydrogen. Now coming to helium. In helium you have 2 electrons. So 2 electrons and 2 protons in the nucleus. So 1s1 is there as well as 1s2. That means both the electrons are in S orbit of the first shell, S orbit of the first shell. Suppose if it is lithium, that means one more electron has to be added. See, in the first shell, you can accommodate only a maximum of 2 electrons. You can accommodate only a maximum of 2 electrons. That means if you have one more electron, that means after helium, lithium is having 3 electrons. Where will it go? It has to enter into the second shell. That is what we can see here. See, that is K, and now it is entering into L shell. So thus, what is happening here? The size of the atom is increasing. As the electrons are increasing, size of the orbit is increasing here. Okay, right. So then next, when you go to beryllium, 1s2, 2s2. That means in beryllium you have in the first orbit 2 electrons, as well as in the second also you have 2 electrons. Okay. So children, first copy this one. Pause this for a moment and copy the whole thing. And even this part, it's very, very important. Most fundamentals. After this we will be dealing with chemical bonding, where you are supposed to know what is meant by valence electrons. Now if you come to valence electrons here, that means electrons in the outermost orbit. Hydrogen, only one orbit is there. That itself is the outermost orbit, and here the valence is 1. Helium, 1s2, first orbit, that itself is the outermost. 2 electrons are there. It is satisfying the doublet rule, so therefore it's very stable. And then 1s2, 2s1, that means what is the outermost orbit? Second orbit is the outermost orbit, where you have only one electron in it. Therefore, this is the valency. Valence electrons are 1. So, therefore, here valence electrons are 2. In outermost orbit, you have 2 electrons. Okay. Chalo, take the screenshot. Let's see. After beryllium, then we are with boron. So, 5, 4 in the 1s and 2s. Here 2 electrons, here 2 electrons, 4 are done. Next it enters into the p orbit, right? Next it enters into the p orbit, and only 1 electron here, so 2p1. So this is like, now see, in the second orbit, you have 2 plus 1, 3 electrons. That means outermost orbit being the second one. That is, if this stands for K shell, this is L, this is M, this is N. So in L shell, you have here 2 plus 1, 3 electrons. Likewise, so see here you can see the electronic configuration of all the elements. Right, coming to neon. So here it is 1s2, 2s2, 2p6. Right, so here 2s2, 2p6. That means in the second shell, maximum number of electrons are 8, and that itself is the outermost orbit. That itself is the outermost orbit. That means it is satisfying the octet rule. Therefore, these are called inert gases, and they do not actively participate in any kind of chemical bonding or reaction. So, most stable element. Then likewise, if you move like that, you have again at argon satisfying the same thing. So here I have written it as, briefly I wrote it as 1s2, 2s2, 2p6, 3s2, 3p6. Now see, after 2p it enters into 3s, then after 3s it enters into 3p. So 3s2, 3p6, 3s2, 3p6. This is the argon octet rule. So thus even this is the most stable element. Likewise, if you observe the Euler diagram, you can see that after 3p, 4s is filled. Then after 4s, 3d. We will enter into 3d but not into 4p. We will enter into 3d. Back again. We are moving into the M shell again back, and then we are trying to fill the electrons here. Then again into the fourth shell. So that is what, where can we see that example? Say suppose if you are entering into the scandium. So scandium, you have 1s2, right, 2s2, 2p6. I have written a second orbit, all 8, 3s2, 3p6. Then afterwards 4s2. Then comes after 4s2, it comes to 3d1. After 4s2, 3d1. Please remember this. Without this diagram, you will not be able to write the electronic configuration. So therefore, after 4s2, you have 3d1. So this is how I have written the complete electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Likewise, now, so you are in the third shell, you can accommodate the maximum, you can reach to the maximum electrons till 3d10. So 3d10 is for zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 is done. After 3d10, what happens? Let's see the Euler diagram here. After 3d10, it is going to enter into 4p now. After 3d10, you have to enter into 4p. Now let us see whether we are able to write that one or not. After zinc comes the gallium. So 3d10 is done, then 4p1. This is how you have to write the electronic configuration. And here, see the check which one. Now we are in the fourth orbit, is it not? Fourth orbit. How many electrons are there in the outermost orbit? Is it only one? No. Why? Because 4p1 is here. Don't forget this one, 4s2. So now 2 plus 1, 3 electrons. These are the valence electrons. Okay, here also valence electrons are 2. Here also valence electrons 2. Right, so you have to see which shell you are in. The highest shell, highest number shell is the outermost orbit, and there you have to check how many electrons are there in that particular orbit. That gives you the valence electrons. Is that clear? Children, now it's your job to write down electronic configuration of. I am giving you the homework. I think I have written till scandium completely, and then after scandium, then you write the remaining 35 elements. Remaining 35 elements. Okay, children. So for 35 elements, you write the electronic configuration and post me. Then I will come to know like whether you are able to write the electronic configuration, as well as if possible write down the valence electrons. Here what are the valence electrons here? Second shell, right? 2 plus 1. Valence is 3. So you can write it like this. Valence is 3. Here valence is 4. Okay. Likewise, you have to write the valency of each and every element and then post me, so that we can start chemical bonding in the next class. Okay, children. Kartikeya and Venkat Sai, it is very, very important to you, as well as Nayana and Shulamiti. So please take the screenshot of this. And then the next half. Right.